This is part 4 of the crude oil and fuels topic. It's GCSE, AQA chemistry, and it's valid for dual and triple award students. In this final part of the crude oil and fuels topic, we are going to take a look at cracking hydrocarbons. I'm going to recommend, as always, that you pause the video as you go, try the activities for yourself. So we need to know why we crack larger hydrocarbons to form smaller ones. We need to look at the usefulness of cracking. We need to look at the usefulness of hydrocarbons, why we depend on them so much. We're also going to look at some of the key differences between alkanes and alkenes, both of which are products of cracking of crude oil. So what is cracking? Well, we need to look at this not in isolation. We need to consider everything that's come before it. Way back in the beginning of this topic, we looked at crude oil being separated into its fractions. We use fractional distillation. There's a whole video on that to go back if you need to remind yourself. But once we've done the separation, we find that we have fractions of crude oil where all of the hydrocarbons within that fraction have similar sizes and similar boiling points. I really want to reinforce that word similar. It's not the same. Petrol might have 6, 7 or 8 carbons in its chain, for example. The boiling points will differ, but they will be similar. We also talked about some of the other key terms that are quite important to us. We know that shorter chains are less viscous. It says here, longer chains are more viscous, they have higher boiling points, and they are harder to ignite. We talked about the trend in flammability as well. So it's important that we remember all of this key information. Now, cracking is something that we do to break down longer hydrocarbon chains into the smaller chains that are actually far more useful. The type of reaction is thermal decomposition. Some questions for you to think about. And in this first one, I'm picking 3 at random, really. I mean, they are 3 of the most common ones that you're likely to come across. So petrol is a fraction. We use that to fuel cars at the moment. We might also talk about kerosene, which is used as jet fuel or plane fuel. And we might also talk about fuel oil, which is used to fuel giant ships and tankers and cruise liners. It's important to note, actually, that all 3 of them are fuels. We are going from petrol as the shortest to fuel oil as the longest. So they are higher boiling points. They are harder to ignite. But actually, the longer chain, if you can ignite it, which a huge ship engine can do, is going to release a lot more energy. Petrol would not get a cruise liner moving, for example. So we've got to be considerate of that when we're deciding on fuels. But that's an aside. Let's carry on with the questions. What process is used to separate crude oil into these different fractions? And again, there's a video that goes through this in detail earlier, fractional distillation. We also talked earlier about the term viscous. What do we mean by it, and what's the trend as chain length increases? Well, viscosity is how easily something flows, and the longer the carbon chain, the slower or the harder it is for it to flow. It becomes thicker, it becomes gloopier, it becomes more viscous. And finally, why do we crack longer hydrocarbon chains? Well, as was discussed just a couple of minutes ago, it's because shorter chains are more useful. We might also think about it in terms of profitability. So in terms of the conditions for cracking, I'm going to recommend that you simply learn this information. We can crack by actually passing the fraction over a hot catalyst. I've put this here because we talk about catalysts in the previous chapter. And also we could mix it with steam and heat to a high temperature. So there's 2 different methods for cracking hydrocarbons. You do need to be familiar with both of those conditions. Some more questions for you to try. So these are about what we actually mean when we talk about thermal decomposition. So when we talk about the word thermal, you might think about your knowledge of physics and thermal energy is heat energy. You might think about wearing thermals to keep warm. You might think about a thermos flask, which keeps drinks warm. So thermal means heat. And the word decomposition, away from science, means for something to break down. If we decompose something, we break it down. So we put those together. What do we mean by thermal decomposition? And it really is as simple as breaking something down using heat. And that's what cracking does. It breaks down longer carbon chains using heat to make smaller, more useful, more profitable chains. Now, one of the big differences with cracking, one thing that we can guarantee will always happen, is that our alkane hydrocarbon chains, when they crack, will also produce alkenes. We need to think about what the similarities and differences are. So have a think, and then when you're ready, move on. So I've got ethane here, C2H6, ethene, C2H4. Similarities. They're both hydrocarbons. They both contain carbon and hydrogen only. They're also both covalent structures. We know that because it's non-metal bonds. And also covalent bonds are represented by sticks in this way. And other similarities, they've both got 2 carbons within their structure. I've got 1, 2 and 1, 2. So let's look now at the differences. And these are really important to note. Ethene contains a carbon-carbon double bond. That's what makes it an alkene. This only has carbon-carbon single bond. So there's a difference there. And the second difference, we can see that ethene has fewer hydrogens. It has 4, whereas ethane has 6. So remember that an alkene contains a carbon-carbon double bond. Now, when you have cracked and you've made alkenes, we can test for those alkenes. And it's an important test for you to be able to carry out and to remember the observations that you would make. So we take our sample of alkane or alkene and we add bromine water to it. We then shake and we note the observations in a results table. Now I've done a results table here. I've got alkane, alkene. Doesn't really matter which one we've used, but what would you observe? Can you remember? So with an alkane, you wouldn't see any change at all. There's a term that I would recommend you use for that, and that is no visible change. Whereas with the alkene, the bromine started brown, but when we added it and it was shaken with the alkene, it decolorized the brown bromine water. The brown bromine water turned colorless. With all of that in mind, now try to answer these questions. And the purpose of this is just a straightforward reinforcement of what we've just seen to really make those connections and hopefully remember it more securely. So what colour is bromine water? It is brown. What happens when we add it to an alkane? There is no visible change. And what happens when we add bromine water to an alkene? It will turn the bromine water colourless. And a really important distinction here, we do not say it turns it clear. Clear means not cloudy. Bromine water is brown, but it's clear. We have to use the term colourless. Okay. Taking another look here, a chance to remind ourselves about the general formula of alkanes, and I've also added the general formula of alkenes. You will need to remember these. You will need to be able to apply them. So if I have got 15 carbons in an alkene, I would have 30 hydrogens. If I had 4 carbons, I would have 8 hydrogens. As we already know from a previous video, if I have 4 carbons in an alkane, I would have 4 times 2 plus 2, 10 hydrogens. C4H10. Finally, to finish off this video and this topic, we're going to look at some equations that do come up quite commonly, where lots of information is provided, but do be careful to read all of that information carefully. Have a go, and when you're ready, we'll move on. So I'm going to colour code these to make it easier. Decane, C10, using the general formula for alkanes, which we've just spoken about, CnH2n plus 2, means decane would be C10H22. We also know that we're making pentane, that's C5H12. We're making propene, C3H6. And remember, alkene, the general formula is CnH2n. Double 3, you get 6. And finally, we're making ethene, so that would be C2H4. When you've done it, check the balancing really carefully. I've got 5, 6, 7, 8, 9, 10 carbons, 10 carbons. I've got 22 hydrogens, I've got 12, 18, 22 hydrogens. It's already balanced. Let's do one more of them. So, dodecane, C12, it's going to be H26. And we are making from there octane, which would be C8H18, and we are making ethene, C2H4. So we've got the equation, but let's check the balancing again. At the moment, I've got 12 carbons, I've got 8, 9, 10 carbons. I've got 26 hydrogens, I've got 18, 22 hydrogens. So that takes us to 2C2H4. That's going to take us to C12H26. And I've got 18, 22, 26 hydrogens here. And I've now got 8, 10, 12 carbons. The equation is balanced. That takes us to the end of this video. Thank you for listening and goodbye.